Most discussions in fluid mechanics deal with single pipes, albeit with many turns, fittings, valves, etc. However, there are systems that have multiple pipes as described below. So the first thing we're going to look at are pipes in series. So here what you have is you have a series of pipes, and each one has a decreasing diameter. So you have a flow rate, which is Q, but because of the continuity equation, this Q, we'll call this Q1, Q2, and Q3, our Q will stay the same. How about velocity? Does velocity stay the same? No, it doesn't. And why not? Well, Q, which is the volumetric flow rate, is equal to the velocity times the area. So if Q stays constant, when the area changes, the velocity has to change as well. So if, as shown here, the diameter is decreasing as we go down the system, then the velocity of the fluid has to increase. So V1 does not equal V2, does not equal V3 in this particular picture. How about head loss? Again, each pipe will have its own head loss based on its friction factor, length, diameter, and velocity. But if you want to get the total head loss, all you have to do is calculate the head loss in each one of these pipes and add it together. So note we're making some assumptions here. The first is that the fluid is incompressible. In addition, we are neglecting minor losses. Now let's look at pipes in parallel. So here we have a total flow rate, Q, and we have Q1, Q2, and Q3. And what you'll find is, again, due to continuity, this Q, total Q, is equal to the sum of the Q's or flow rates in each one of the pipes. However, if the energy balance is done over the whole system and the head loss encompasses all the pipes, what you'll find is that the head loss in pipe 1 is equal to the head loss in pipe 2, which is equal to the head loss in pipe 3. Finally, we have what is known as a loop, as shown here. Again, we have a Q1 that comes here and divides into Q2 and Q3, so our Q1 is going to be equal to Q2 plus Q3. Don't ever make the assumption that Q2 equals Q3. Occasionally it will, but there has to be something in the problem statement that tells you that. And by the way, these little triangles here mean that the pressure at the top of that system is atmospheric pressure. So if we call this A and we call this B, and we apply the energy balances for the two pipes between A and B, look at what we get. If you note, everything here is the same except for these two terms, and therefore our head loss in pipe 2 has to be equal to the head loss in pipe 3. There are even more complex systems. For example, let's look at a 3-reservoir system as shown below. What can make this more complex is figuring out which direction the flow rate is going in or out of each reservoir. So although the focus in fluid mechanics courses is generally on single pipe systems, it's good to have some basic knowledge on how multi-pipe systems work as well.